I thought it was really, really informative. I don't know if you guys probably don't follow this, but the Nobel Prizes, they just announced all the Nobel Prizes. Um, Nobel Prize in physics went to a computer researcher. Nobel Prize in chemistry went to a computer researcher. I mean, for me, not that I don't appreciate artificial intelligence and stuff like that. I use it all the time in my work. It's great. But this to me just speaks to how stuck a lot of these sciences are, particularly physics. It just seems completely stuck to me. Um, and it's really fun because we don't actually have a physics department here, so I can pick on physicists all I want. Nobody's going to stop me. And my background's in physics too. I love physics. I don't think that obviously I don't think it's the entirety of the universe, but I think it's a really interesting approach to reality. But it's so interesting what you mentioned about the atom, the subatomic particles, and how this word particle doesn't actually describe physical objects, but describes these dynamic measurements of something that's reproducible and predictable that we can see time and time again. And it has this energetic quality. It has other qualities which people don't even bother understanding what they mean, like spin, right? And spin's going to be really important when we start talking about what light is. But these qualities just get bundled together and they get jammed into this matrix of information, which we call a particle, essentially. And so the atom is actually made much like a computer software, right? Much like a computer program, out of these bundles of information. Our modern quantum theory is much less a material representation of what an atom is, and much more something like a software program that tells you how the atom will behave under different circumstances. And that's all well and good, particularly for designing technology, right? I mean, we have incredible, telecom abilities, and our electronics are fantastic because when you put all this information in usable formats, you can reference it nicely. But we're not that much closer than we were 150 years ago to having any conception of what's going on down there below the actual touchable surface of an atom, right? So you can use these incredible microscopes. I actually got to work with one quite a bit when I was in grad school, where you basically take a silicon wafer and you fabricate it in such a way that it only has a couple of atoms at the tip of this cantilever, basically. And you can kind of vibrate this thing across the edges of surfaces that are really tiny, and you can get atomic level resolution. But all you're really seeing is the repulsive boundary of the atoms that are down there. You can't really get past them. The same thing's true. You might have seen like these electron microscope pictures as well. The same deal, you're looking at the sort of conductive boundary, right? Where what the chemists would call the electron shell, but it's really just kind of the edge of where we can pick into. And I have a sense that really trying to come up with structural models for the atom is going to be a complete revolution in physics, but it's not happening right now. And there's something really strange about the way that we do science right now, where people are rewarded for kind of studying the same thing over and over again. And it's not entirely clear how we get out of that. You got to think back when people started studying all these wild new things. Remember, they weren't professional scientists, first of all. And oftentimes, for the money that they did need, they were given money privately by individual patrons and so forth. And so, there's some antecedent for how that might change in the future, but I don't see it when almost all scientists are paid by these giant state bureaucracies to do very incrementally technologically useful tasks. How do we improve this device, this semiconductor, or whatever it is, to really interesting choke points. And of course, what you bring up, the language really matters, right? Most people don't even realize that's a problem because they hear the word subatomic particle and they think, oh, like grain of dust or something, right? Never mind the fact, how the heck does a grain of dust go around this other grain of dust at the center, and why are they even doing this dance in the first place? But you don't really even get that far because the language of the word particle is so hypnotizing, right? The words that we use to describe our world really inform how we look at it, and that's pretty nuts. Did you have a question? No, sorry. I can never tell if the stretching itch thing, whatever. Cool. All right. Anybody have thoughts on the atom? We're going to keep grinding up against the atom. In some sense, our whole universe is half atoms and half something entirely different. And there's been a lot of progress in the entirely different stuff in the last 50 years or so, but not a lot of progress in the atom side of things. which is really shocking. I think people back in the 70s would have thought we'd have all these flying cars and we'd be colonizing, we'd have, vacation homes on the moon and stuff by now. I think it was pretty well understood that that was going to happen, but those advances of the atom, right, of real material science and transportation and stuff like that, they never really happened for some reason. And it's worth contemplating what's up with that, because you guys are going to inherit the earth and the country. It's on you. All right, how about Bella? Are you here? Yeah, hello.
I thought the pendulum for the rotating was really interesting about the theory was like it would have kept the same momentum, but if the Earth was rotating rather than stand still, that it would change.
Yeah, that's a good idea.
But I don't know how that was.
Yeah, we didn't talk too much about that, but it was kind of tangential to our discussion of clocks and like what a clock is as well. I mean, it's funny how so many of these these world-bending scientific experiments didn't require Large Hadron Colliders and stuff, right? They were just somebody who was just like, I think I can demonstrate this principle to be true, and I don't, I just need a pretty simple setup. Now, he actually had a kind of expensive big pendulum, but it's not this high-tech device either at the same time. Pretty interesting. All right, how about Gabriella? Are you here? No. How about Kat? Dropping like flies. How about David? Yeah.
Some Newtonian keywords we covered were mass, matter, quantity. I figured out what latitude and longitude were because I don't know many things in this world, so that's why I'm here. I learned that Greenwich is right between the U.S. and Europe. What's the notes I got?
All right, let's talk about the Newtonian keywords. Were those do those seem like what you understood them to mean in the first place?
Mass, matter, quantity. Might have to get a refresh on some of
Well,
that.
that's cool. I mean, I just think that the mass one in general is another one. It's another one of those situations where the way we use it, informs how we understand it. And the idea, I think mass is actually one of, hand in hand with subatomic particle is another extremely abused word, right? Because if you open a standard physics textbook from high school or something, they're actually moving masses all around. They treat them like proper nouns, right? Or not even proper nouns, but just as nouns, right? So mass is actually a quality that's exhibited by some amalgamation of atoms of some sort, right? It has mass because it's attracted gravitationally or inertially to other things around it. Now, can you move a quality around? I have, let's say, a lot of respect for you guys for showing up here every class and suffering through these, knowledge bombs. But can I hand you my respect and have you take it for a walk around the block, right? In physics, you can only move physical objects around, right?
The atom, inside an atom, since that was kind of that.
Well, with the atom, my point is that we should probably have a physical structure for the atom, and if we want to make real, true progress with understanding how these things unfold properly. But the minute that we start taking their qualities and applying motion to their qualities, we get ourselves down a real rabbit hole, because it's like, what are we actually talking about at some point? It's very difficult to have a physics presentation without physical actors, right? It's difficult to have a story without actors in the story. Can you imagine going to a play with no actors, right? You actually can't imagine it. It's not possible. Actually.
That was my literal answer.
Yeah. You can't do it. But in physics, we do it all the time. This is my point. And to some extent, we can blame Newton for this, because he gave us the force, which is an abstract actor that's not actually physical at all. And the forces do things all of a sudden. So we have a play now that has a bunch of forces doing stuff. Well, what the heck's a force? I don't know. It's just the quality that's imbibed. It's an effort that's applied by somebody who, I don't know, it doesn't matter really necessarily. So it's these are very productive when you're trying to design a catapult to destroy your neighbor's village or something like that. Is you can qualify the catapult and the amount of force it generates, and it's very technologically productive to a point. The same with the concept of mass. It's very technologically powerful to a point. But the sad part of it is that that language starts to, especially the more that we treat these abstractions like physical bodies, this is actually a fallacy in philosophy called reification. Check it out. You can look it up. It's a good word to impress your friends. Reification. It's when you misplace the concreteness of something. It's like if I were to like put a map up on the board and I was like a scavenger hunt or something, and I was like, okay, let's all meet at the starting points. And it's like a map of the university or something. And then the starting point says like the library or something, right? But it's drawn as an X up here. And then everybody in the room comes and stands up here because they think that we're talking about this being the reality of the situation, but it's a map of the situation. You're supposed to go to the library, but you think you're supposed to go where the X is, and the X is on the board, right? So this kind of thing, it seems trivial, but the more that we keep talking about this idea, I think you're going to see that it is fundamental to a coming paradigm shift in the way that we actually do physical science on this planet. And I think that subsequent generations are going to hammer through this problem to the point that they're actually able to come up with good structural explanations for things like light and gravity that we essentially treat like magic, although we have incredible mathematical formula to describe how they unfold. We have absolutely no physical concept of what the atoms are doing to affect these apparently magical looking processes upon one another. So mass is just another one of these terms. What does mass mean? Well, to most physicists, it's a parameter that you input that describes, how something behaves in a gravitational situation or an inertial system. Okay, well, what does that actually mean, though, about the atoms? Like, what in the heck are my atoms doing here to develop the quality of mass? What's happening? Like, what is going on between this atom and all the atoms underneath it that makes it want to fall down to the floor? Something. And so the same could be said about so many of our fundamental everyday things. Light, for instance, is another one. Magnets, right? Magnets, how do they work?
I don't know.
Right.
It scares me.
Right. It should scare you. And the funny thing is, if you go on the internet and you start reading about how magnets work, you know what they're going to tell you? They're like, you can go to your favorite Ivy League physicist. Trust me, I've done it. You go to them and you say, how do magnets work? You know what they tell you? Tell you that atoms act like tiny magnets, and so the little tiny magnets build out bigger magnets. I'm like, really? This is the best you guys can come up with? You've got to be kidding me. But the reality of the situation is that those sort of stand-in, they're like sort of a stand-in for an explanation, but they work good enough that we can build stuff. And as long as we can keep building stuff and make the iPhone 6000 or whatever, it's not really a national priority. It's not really what people are in the business of doing as far as advancing what we consider science and technology. By the way, I think that the ancients would have had a very different conception of science versus technology, and I think that's almost been entirely lost today. Because today it's like, if you can't do something that's technologically relevant, it's not really going to get any funding in the science world. But science is really just about understanding. It's just like, hey, how does nature do this magic stuff, right? At some point, like every single culture like came upon this idea that, hey, wait a second, maybe it's not just magic. Maybe there's actual reasons for stuff, whether it's the day and night or atoms sticking to each other. Like there's got to be an actual mechanistic explanation for it somewhere. That's what science is. But when these states start getting enormous and start dishing out all the money, then they want something back for that effort. They don't just really care how things work. They want to know, what can we do with it? How are we going to make a better laser-guided bomb or whatever it is? So technology, science, different concepts, they feed back on each other, but there's not a lot of room left for basic science in the universe we inhabit today, or in the world. All right, cool. I guess I'll just keep rolling. We'll pick up some more attendance points next time. I do want to make sure that we have time to hurt ourselves on the climate topic, which is always fun. So in order to get there, we need to make it past time. Did anybody have any thoughts about time? This is so much more fun if you guys talk to me. Yeah.
I guess from a philosophical standpoint, like time has always existed. But for us to understand it, we had to use clocks, use the sun, but like time was always there.
Like change was always there, for sure. some stepwise change. Yeah, I think you're probably right about that. Yeah.
I've always heard it as being like not linear and past, present, and future all at once.
It's kind of what it's like being a human being. That's for sure. I think there's some truth in that. I think that there's something really singular about being a human being that's different from being other animals. And I've watched a lot of animals and worked with a lot of animals. But we do seem to always have a little bit of the past and the future with us at all times. You know, we're not always totally there. It's actually, I think that's why like the whole meditation revolution and so forth is all about trying to just try to be in the present. It's really hard to do. Actually, even like as I'm giving this lecture, I'm like, it's hard for me to not think about like, oh, I got to do this thing afterwards, or like, oh, did I do that thing right this morning or whatever. So it's like we are kind of time machines as human beings, which is really strange.
I was just thinking about how interesting it is that time is like it always has been and always will be. And so like there was something going on like 300 billion years ago right here in our solar system, you know?
Well, I doubt the solar system was here 300 billion years ago, but I'll roll with it.
Well, it's just it was just then I started thinking about like why there's some sci-fi thing that's like 300 billion years ago, but they're more technologically advanced than we are now.
Star Wars. Have you seen Star Wars?
Yeah, of course.
The original ones? I think that's how they start off.
I thought it was just like a long time ago in a galaxy far away or something.
But it's more futuristic than here.
Yeah, true.
I don't know. It's sort of that same ilk. There's actually this. You guys ever heard of the eternal recurrence paradox before? You guys haven't read Nietzsche? You have? Yeah. All right. What do they have you guys reading? You guys don't read Nietzsche in college anymore? What's going on? No, Nietzsche was a terribly bitter man, very resentful, but very interesting and fun to read. Nietzsche had this idea. He was like, this is before Big Bang cosmology and everything, which we can pick on later. But he had this idea that if time was eternal, right? If time kept going forever, never mind where it came from in the past, but if this was the case, that there was no end of time, and he couldn't come up with a good reason why there should be an end of time, just sort of like you just did, he said, well, technically, all of this is going to happen all over again at some point, because the universe will run out of possibilities. And he called it, other philosophers refer to this as the paradox of eternal recurrence, which is sort of like things inevitably must repeat themselves, giving an infinite quantity of time. What do you think? Buy it? Hey, what's that?
So I've done drugs before.
Yeah, I've done drugs.
There was a really funny episode on like Family Guy talking about this, and it was like they went so far, like Brian and Stu, I think, went so far into the future, and there's Christianity all over. Christianity again?
Yeah, that does seem to happen. There are cycles we go through, which is quite interesting as civilizations. It's really, really fascinating.
I think the same thing was in like a Rick and Morty episode.
Yeah.
It's so funny, these cartoons are like mining these 18th, 19th century philosophers. But it is intriguing. And the thing that I wanted to impress upon you is like you all have really interesting ideas. You had an idea too about time in the back, yeah?
Well, I just was thinking I'm like pretty far behind everyone right now.
It's all good.
There was like something that was talking about how like when you look into space, you're looking back in time. And if it's so casual that is true, like would there not be an equally like available way to look at the future?
So the reason that your textbook says things like when you look out into space, you're looking back in time is because light has some travel speed to it. And so the light that's reaching us now was emitted at some time in the past. Now, for something that's, billions of light years away, which you probably can't see with your naked eye anyways, but let's say hundreds of thousands of light years away, what you're actually seeing is photons, or let's say light that was emitted from those atoms hundreds of thousands of years in the past. As far as the future, somebody in the future is probably staring at us right now, 200,000 years in the future or something on the other side of the galaxy, if you're willing to entertain the idea that there's probably other well, I suspect personally that there's other intelligent life forms out there, perhaps. At least it seems possible. It's a pretty big night sky. Have any of you guys ever seen the night sky away from cities and stuff? It's hard to look at that place without thinking there's probably stuff going on we don't know about. I don't know, not to get too deep into the aliens thing, but we'll actually have plenty of time for that. We have a whole lecture for that. But because we're desperately looking for them, by the way. You know, we're not waiting for them to show up on our doorstep. We're actually very much interested in trying to find signs of life out there. But, okay, it's a huge place. It's also a very long place. So given eternity, there's probably going to be other civilizations that rise and fall. And so maybe there is some future situation where people are looking back on what's happening. Well, they're probably almost certain. I don't know. I feel like they almost certainly is. Yeah.
Then if you travel outside of the atmosphere, you're technically traveling back in time. Are we the only thing happening right now?
No, I wouldn't say that you're traveling back in time outside of the atmosphere. I would just say that the light, comes down to a confusing way in which we talk about distances using light years, essentially. That the light itself takes time. Even the light from your face to mine right now takes some minuscule amount of time to happen. So your perception of me is slightly in the past. You're seeing some nanosecond delayed version of what's actually happening up at the front of the stage right now. I don't know if that helps. But look, the nature of time is fascinating, and from a philosophical standpoint, it's even more fascinating. The reason that I want to talk about this, though, is to remind you guys that in physics, it just means something pretty boring. It's sort of like the comparison of some regular motion that's completely predictable, that happens over and over again the same way, like the day and night cycle, or the year, or a clock. It's something very periodic that we compare to other motions in order to gauge, really, with respect to that standard motion, if it's faster or slower, and how much faster and slower, right? So that's all that these clocks really are doing. And I think that I ended the example with kind of an interesting point, which is like, you know, you take that grandfather clock up to Mount Everest, it slows down. Did time slow down? I mean, according to physics, technically it did. But is there anything like crazy about that, or spooky, or weird, or otherworldly? Like, not really, honestly. And so, you know, I see these headlines all the time. Actually, they've been busy with other stuff, but you see these headlines where they're like, GPS satellites prove Einstein's general relativity, that time slows down in these gravitational wells, right? Well, it's like, okay, what is the clock they're using? It's not a pendulum clock, right? It's this thing called an atomic clock, all right? And what's an atomic clock? Well, it's just an atom. It's actually a bunch of atoms, but it's essentially could be boiled down to what an atom is doing. So when atoms vibrate, they have some predictable wavelength of light they give off. And when they go into different energy states, they have different wavelengths of light. So there's something called like a ground state or a rest state of that atom. It has like a normal kind of light that it's always kind of churning out. And we're not going to get into what light is at all. But, you know, what happened was they actually had a communication satellite up in space, I think back in the 80s or something. And they're supposed to be in these nice circular orbits around the Earth. But this one broke for whatever reason, and it started drifting like into this highly eccentric orbit. So it would go very elliptically, right? And as it came in closer to the Earth, they noticed that actually the time would seem to slow down on the thing. The clock would slow down. And they thought, oh my God, this is amazing. And it obeys the laws that Einstein predicted. So the conclusion was that time was slowing down near the sources of gravitation, which is actually entirely reasonable as long as you understand that what time is in these physical equations is what clocks do. Now, you might think, why in the world is the atomic clock slowing down? Well, the same reason the pendulum clock is behaving differently in different gravitational situations. So what happens? Well, you take an atom and you put it around a bunch of other atoms that are all pulling on it. So if I took all you guys and crammed you in an elevator, and I asked you to do a bunch of jumping jacks, probably have a pretty hard time doing it, right? But if I told you to do some jumping jacks here, Some of you would be maybe better off than others, but like we could all do jumping jacks, right? And so I think something very similar is happening with the atoms. They're under a lot of pressure when they're in groups and they're crammed in together. Gravitational pressure, that is tension, so a negative sign in front of the pressure, but it's still a pressure. And they predictably, according to an inverse square law that Newton figured out, maybe 400 years ago, that pressure dissipates as they move apart from one another. So there's nothing unusual or spooky or mystical about the fact that time, let's say what clocks do, slows down, right, in the presence of large bodies and so forth. This makes perfect sense. They absolutely should, because the way that we design our clocks more than anything, and the way that we design our clocks reflects the way that gravity works amongst groups of atoms. And those equations are really solid, so there's no reason to believe that it shouldn't. In terms of the philosophical business of what time is and whether, you're gonna age differently or so forth if you go and sit next to a huge pile of atoms, like at the center of the galaxy or something, I don't know about that. Probably have a hard time hanging out there anyways. Yeah.
I think this was in the movie Interstellar.
Yes.
They like flew out.
Yes.
to
Yes.
the planet.
Yes.
Like, what is up with that?
Yes.
Is that even real, or is that still hypothesized? Or-
Well, that's like exactly what I'm getting at, is that like if you take this principle, like, all right, this is what's so funny is that, these words, mass, time, particle, everybody just acts like they know what they mean. Which is crazy because we don't actually sit down and talk about what the heck we mean. And if we did, well, the sci-fi would probably be a lot less interesting. But the reality of the situation is a lot of these concepts were invented for science fiction. You guys too young to know who Carl Sagan was? Yeah, so Carl Sagan was he's a really cool dude. You should watch some of this. He had this program in the 80s, I think it was called Cosmos, and Neil deGrasse Tyson took it over. Anyways, Sagan actually was writing a book called Contact, which got made into a movie. Anybody see the movie? Jodie Foster? Yeah, you guys are so young. It's actually a pretty good movie. But it's similar, right? He needed a way for her to go back in time and visit her father, I think it was. So he actually had the idea. He was like, well, clocks slow down in the presence of gravitational fields. So anyone could get the clock to go backwards. And so he goes to his buddy, I think it was Kip Thorne at Caltech. I think it was at Caltech. And he's like, hey man, like, how could I make this happen? Like, is there any way you can torture these math equations until I can get so much mass in one location, right? So much gravitational pull that the clocks start to go the other way. And he was like, there was actually this one solution that was advanced as an argument against Einstein's general relativity about this thing called a singularity, which is, for lack, to just cut to the chase, it's sort of like where the Einstein's field equations stop working, right? So you get this infinity that arises in the equations. So they invented the black hole for the novel, which became a movie. They invented this concept of wormholes. Of course, black holes are basically a mainstay of astrophysics now. But they started in sci-fi, right? Wormholes started in sci-fi. Yeah.
So was that the first time travel movie?
I think they had the time machine movies before that. There was one movie I remember in black and white. I couldn't tell you what it was. It was around the time of like The Invisible Man and all that stuff. But it was the first time someone tried to come up with a scientific justification for it. Exactly. So, yeah, I'm not trying to break your heart about time travel and stuff like that. But I do think it's important to keep our science fiction separate from our science. And you're probably not going to get that in the headlines. So, for the purposes of our conversation in the physics realm, in the world of atoms, time is what clocks do. Each clock kind of has its pluses and minuses. They're all in some sense affected by gravity. So this is something we don't seem to be able to get around. What else do I want to say? I think that's it. Another way to think about it would be that, and someone mentioned this already, that like change would keep happening even if humans weren't here. But if humans weren't here to notice, I'm not sure that there would be really any time, because for time you kind of have to have a memory. In other words, you need to have a periodic motion to compare something to. you need to remember where the clock started at in the first place, right? It's definitely a measurement system that we've concocted for ourselves here to adjust for how fast or slow things unfold. But it's also doomed to remain in that realm of human constructs as well. So we got to be really careful with that one. If you guys stick around next semester, it's going to rear its head again because in astrophysics, we have merged change and space, so locations and rate of change, into one kind of unified abstraction, which is called space-time. And this, of course, leads to a whole nother slew of nightmares. But that's where we're at today. So we'll talk more about those as they crop up. I want to talk about a couple of different ways of measuring the day. This is somewhat interesting. People have had a really hard time with this actually in the past. So there's the obvious way of measuring the day, which you guys are familiar with, which is that Earth turns around and all of a sudden it's facing the sun again, right? It's been a day. The problem is that you could do the same thing with a star, right? You could say, I'm going to turn around until I'm facing that star again. Now, the problem is that those 2 days actually have different lengths, which is a real problem for navigators and so forth. So why does that happen? It happens because, so the sidereal day is actually the star day, and the solar day is, of course, the one where you're facing the sun again. So this is kind of interesting, that every day it's actually a degree off, because if you think about it, the Earth's kind of not only turning, it's also orbiting the sun. So it's kind of moving a little bit into the sun every day, right? You can imagine it kind of leaning into it as it turns every day. The result of that is that, again, it's pointed a little bit more than where it should be necessarily. So the solar day is slightly longer as a result of it, because it's got to turn a little bit more towards to get back to pointed at the sun. Kind of weird. So that's about 4 minutes a day that it gets off from the actual sidereal calendar. Yeah.
Why do we have like a leap year?
No, but we are going to talk about leap years too, which is actually really funny. We're almost there. So there's also apparent solar time. So this is kind of interesting. It's like this basic sundial. It's like, well, the sun is directly overhead, so it's noon. Now, what's the problem with having apparent solar time everywhere you go? Well, if I'm on one side of town, noon's going to be at a slightly different time than if I'm on far side of town, right? And this multiplies the further that these locations are set apart from each other. Now, for most of, like, let's say modern, like, European timekeeping history, every town actually had its own clock. Like, this is Big Ben in London, obviously, one of the more famous examples. But most of these old towns, if you go visit these places in Europe, there's often a clock in the center of town. That's because each town would have its own solar time that it would go by. They would set the clock based on noon when the sun's directly overhead, and that's how they kept track of time. And, you know, that was perfectly fine for hundreds of years from what I can tell. Nobody sweated it. The problem happens when you start using Zoom calls and telephone calls and you're coordinating stock exchanges and all of this stuff. And so the result of that is that they had to standardize it. So they took an actual average value of the solar day across the year and made this 24-hour standard that they could apply across all of these different places, and they chopped the world up into time zones. So this happened in 1883, which wasn't that long ago, but 150 years-ish ago. Now, what's interesting about these time zones is, for the most part, they make sense. As you travel across the United States, for instance, it's like, it's not that big of a deal. Like, you have to drive quite a ways to get into a new time zone, and then quite a ways further. Some places, though, it's pretty bizarre. Like, look at China. China's on a single time zone, but China occupies a great deal of physical territory. And the result of that is that if you're at the, say, western edge of China, so in Tibet, occupied Tibet, however you want to look at that nightmare. Tibet, the sun rises around noon, right? When it's rising over in Beijing at like 6 in the morning, right? Because this time zone stays the same no matter what. But the sun doesn't obey the time zone, and for whatever reason, that works for them. I can kind of see that being useful to some extent, unless you're, working a email job or a Zoom job and you got to get up at 8 a.m. wherever you are. That might be a nightmare. So the countries have kind of decided how to join in on this on a case-by-case example. We also had to arbitrarily set a date line too, right, where the day starts over arbitrarily. They picked this line that went right down the middle of the Pacific Ocean because, any guessers? So there's not a lot of people living in the ocean, I guess. So it would affect the least number of people was the idea. It's really funny though, I'm constantly dealing with people in Australia and I can never tell what day it is when we're trying to plan our meetings. It's like, I'll see you next Tuesday at 4 p.m. I'm like, I just can't do it. I gotta like count to a different date on the calendar and so forth. Very confusing. So the date line is there. That was established to deal with this situation. Now, as we start to walk towards this climate discussion, we need to talk a tiny bit more about seasons. Yes.
Going back to the date line.
Okay.
It's really interesting to travel, like going over the date line.
It is weird.
Last year I came back to the US and I got back before I left.
Where were you coming from?
I was coming back from South Korea.
Okay.
And so it was really crazy because I was like, I've been traveling for so long, but technically, got home before I left.
Yeah. That's crazy. Yeah.
I was so afraid I missed like a whole day going back over to Japan. He was like, I missed my Duolingo streak.
It was gone. Oh, really? Oh, it's horrible. I was doing Duolingo for a while too. I kind of fell off the wagon though, unfortunately. Yeah, once you lose your Duolingo streak, it's like, who even cares anymore? How bad did I really want to learn Russian? Yeah, no, my whole wife's family speaks Russian, so I really got to learn it soon. Okay, so this is the seasonal situation. We talked a little bit about this. Guys, if you learn anything in this class, why is it hot in the summer and cold in the winter? Yeah.
Because we're closer to the sun.
We're not closer to the sun. We're tilted towards the sun. Yeah, sorry. Just jump into the chase here. We're not closer though. We have more insolation. So not insulation, but insolation. So more sunlight is effectively reaching us. The Earth being at a tilted angle as it moves around the sun, the southern hemisphere at some point is getting more, and then the northern hemisphere is getting more sunlight, depending on, because remember, that tilted thing moves all together as one body, essentially. And you can see an illustration of this up here, which hopefully should illustrate what's going on a bit more. So the distance to the sun is varying very, very, very little. And in fact, we in the northern hemisphere are actually closest, we're closest to the sun in January. The Earth is closest to the sun in our January, yeah. But I guess it's January for everybody, it's just summer there, yeah. There is, yeah. So it's an ellipse, but it has a really, really low eccentricity. It's darn near a circle. It's something like 3%-ish closer, which is actually nothing compared to this effect. So as we're tilted more into the sun, we're actually getting more rays per unit area here. So you can see that the rays kind of, they come straight down in the summer. And of course the days are longer as a result of this tilt, right? So in the winter, you guys kind of notice this, everything's kind of shadowy in the winter, right? Everything is kind of long, the shadows are all long. So the sun's rays are actually spreading out. It's all about how much radiation you get at the end of the day. That's what determines how hot or cold it is for us. Short days and spread out rays is a good way to remember it. Now, the spreading out is actually quite interesting too because the atmosphere really eats a lot of light too. And so if you can imagine, you have this atmosphere above you, but it's also extending in every direction to your sides, right out to the horizon. If the sun's coming down, like say at sunset, why does the sun turn red at sunset? Well, all those rays have to go through a lot more atmosphere. And so they're much more likely to get deflected by all of the atoms in the atmosphere. So that scattering is actually what reddens the whole situation for us. Do I want to talk about this? I think we've talked about that enough. Let's talk about that. So it's interesting, if you are like summer down south, right? For South America, for us, it's winter. Now
I just had a quick question.
Yes.
So when it comes to like Earth-directed solar flares, would that be more impactful during the winter or the summer due to, I guess?
Well, it depends who you're talking to, right? So people down in the south, right? During our winter, it's summer for them, right? So they're probably, in some sense, going to be more exposed to that kind of thing. Solar flares, that's going to be more next semester. Solar flares are a really important topic, but we don't have time this semester. Stick around. But yeah, it's interesting. You gotta remember, actually, when it's winter for us, it's summer for somebody somewhere. And that's actually really, really profound to think about it. But the result of it is, if you look at the way this is working out here, so the tropics, we define them as kind of the north or southmost point, where in your own summer, the noon sun is going to reach directly overhead, okay? But the result of that, so this is summer in the south, right? This is winter for us. You notice that the North Pole is getting almost no sunlight ever, like all day long, which is really crazy. However, look at the South Pole down here. Sunlight all day long. I actually pulled up a movie of this. This is, I think this is winter solstice and summer solstice, full 24 hours in Norway. So sun never goes down in the summer. And sun never basically comes up for a second in the winter. So that's pretty crazy. I had a friend worked in a lab for a while at UCSF, and she went to grad school up in the Netherlands, which isn't even as far as Norway, to the north, and it was extremely depressing for her living there, just because you can't sleep in the summer and then sleep too much in the winter, and it's just very difficult. So that's pretty wild. Now, if you go all the way to, I think we got a movie here. If you go to the North Pole, it's a lot more extreme. So this is the North Pole at summer, and you'll see the sun is just following the sun around the sky. It never actually goes down, which is just kind of nuts to imagine. It just sort of kisses the horizon and moves on. Let's see if we have one. I believe this is, this is, I think, at the South Pole. Same thing, okay? All right. Now, we talked a little bit, this is a bit out of order, I apologize, but we talked a little bit about the atmosphere just now, about the reddening of the sun. This is particularly problematic when it comes to trying to figure out where stars are located at, because the same thing that happens at sunset with this refraction business, it happens when it comes to locating positions too. Any of you guys ever go to a creek when you're a little kid and try to grab a fish that's going by, and the fish is your hands are in the wrong place all of a sudden, right? Because actually the refractive index, so the way that light is relayed amongst the atoms inside the water, is different than in air. Significantly different to the point that it's very hard to grab something between the two interfaces. We have the same problem in astronomy because there's a refractive index for this atmosphere and there's a totally different one for the near vacuum of outer space. And so it's very difficult for us to actually take a telescope and tell you where something is precisely because there's some refractive business going on. So you often find these massive telescopes positioned on top of mountains in the desert, ideally on a mountain in the desert because there's less atmosphere in either one of those situations. So I wanted to illustrate that effect to you as well. There's also this really funny attribute too. I don't know if you guys have been alive long enough for this to occur to you, but the hottest days of summer, they're not really on the summer solstice, right? It's kind of weird in a way. You guys know why that is? Come on. Come on, just give it a shot. You guys.
That like, over, like, I'll just use summer because winter is like the
Yeah.
opposite effect, but over the summer months, like, you're gonna get more and more, as you think about it, like you're accumulating more and more radiation from the sun over time. And then at night, you're like basically dissipating that. But in the summer, it's at a, like you're dissipating doesn't happen as quickly as you're accumulating. But when you hit your peak, you haven't accumulated all the radiation that you could for that summer yet. So like even after, you're still at a effect where you're accumulating more radiation quicker than you're dissipating it. So temperature doesn't start cooling off until the dissipation happens quicker than the accumulation.
Yeah, you pretty much nailed it. I mean, you're not really like taking all those photons and putting them in a bag, but you're heating up the Earth, right?
Yeah.
You're heating up the atmosphere, you're heating up the water. The water is a huge keeper reservoir of heat. Notice that I'm veering into the reification territory when I start talking about storing the abstract concept of heat. This is a big no-no in some sense. But the reality of the situation is you're jiggling all those atoms. They got some motion that gets in them, right? This is heat. We now know that heat is a kind of chaotic motion of atoms. So the atoms get going, and it takes them a while to get going, and it takes them a while, and it takes them a while. And so as you keep putting all of this radiation into it, you're jiggling and exciting all those atoms. You're storing that heat in the Earth itself. And so the result is that the temperatures actually lag behind by quite a bit. I've noticed it by about, I think the hottest time is probably August, honestly. What do you guys think around here? Certainly the river is primed in August. I love going out into the Illinois and stuff. So there's a word for this. It's another one you might impress your friends with. It's called hysteresis. So hysteresis is the lag time between some impulse and when you get an output from it, right? So that's something to keep an eye on. And hysteresis is a really important concept that's going to keep popping up in all of our discussions. So get cozy with it right now. It's really funny. I got time for this one. So the concept of heat, I just kind of casually mentioned that the atoms are jiggling and stuff. That's a pretty new idea, actually. So what do you guys think that they believed before that? Before they realized that it was atomic motion, which is called the kinetic theory of heat.
God.
I mean, maybe, but they had like some sort of nascent, underdeveloped idea before this. It's actually funny because it's very similar to the way we think about electricity today, which is very prescient. They thought it was some sort of magical fluid that flowed, right? So actually, it's not an idiotic idea. And this is another example where the mathematical equations for fluid flow work really, really well for heat. They actually work perfectly. So if you assume heat is a fluid that flows between substances, when I put this cold substance next to this hot substance, something is going to flow between those bodies at a very predictable diffusion rate that's identical differential equations to the flow of, say, diffusion in chemicals in solutions. And you can calculate the heat exchange. But it's totally wrong. Pretty cool. Yeah, questions? No, all right. So they thought it was like a little magical fluid. Now, which is, by the way, very much how we think about electricity today. It's these flow of these little bowling ball electron thingies, which magically, how does a little bowling ball, like what makes it want to go from one place to the other? Nobody knows, don't worry about it. But there's probably something very similar going on with electricity. It turns out the atoms were doing stuff to each other, right? The motion of the atoms was actually what was being transmitted between hot and cold bodies. Probably something very similar with electricity, just a different kind of motion. So, magical fluids. By the way, how did they change their mind about this? I don't expect you guys to know this one, but the way they changed their mind about it, and I think that this is an experiment I would love to do actually with electricity. I'm kind of mixing metaphors here, but go with it. The way that they figured this out was these guys, one of these, remember, people, scientists back in the 1800s, they were not professional scientists, they were doing other things. One of them was, one of these scientists who figured this out was, I think he was in the military and he was working around cannon brigades. And in some sense, he was well acquainted with the manufacturing of cannons. And the way they make cannons, they have these huge drill. They get a big block of metal, iron, and they drill out the cannon, the bore of the cannon, basically the hole that you stick the cannonball in. And he was watching this, and it struck him that this process by which these drills would overheat, that he could essentially generate as much heat, as long as he could keep that drill bit moving, he would never run out of heat. So the idea that the cannon possessed some quantity of this magical fluid called heat, or they actually called it caloric at the time, which we get the term calorie from today, he realized that this was an inexhaustible source of heat. Friction, in other words, drilling of the cannon bore, was an inexhaustible supply of heat. And that as long as he had a big enough block of metal, he could drill it forever, and he would never, ever run out of heat particles. And he realized that that was preposterous because each substance should only have a certain amount of these particles inside of it. Now, that's a really interesting argument to turn towards electricity. I know this is getting a little bit in the weeds here, but I think it's kind of good for you guys. So electricity too, there's an experiment that I really want to do. This would be a really good YouTube video or something. But you should, in principle, each substance should have a limited number of electrons according to modern chemical theory. I don't think they do, but that's the standard model, is that they do. So if you could come up with a way to, like, through, say, you guys ever do that experiment where you take a balloon and sort of rub it on your hair, and a static charge generated, right? So the idea in like the textbooks or whatever is that some electrons are getting pulled off of one, put on the other one, right? And that's how this charge builds up. Okay, so you could do an experiment like the cannon boring experiment, where you rub, say, a piece of wool against something like a piece of amber, which should be extracting electrons from the one onto the other. And at some point, you should run out of electrons. But if you could demonstrate that you actually never did and that the charge flow was continuous, then you might be able to prove that it had something more to do with a particular motion of the atom than it had to do with these actual little bowling balls flying around, which someone's going to do that experiment, I promise you, if I don't get to it first. It's going to happen. It's going to be a revolution, too. Okay. It's a little bit tricky to negotiate because you have to insulate the one from the other and you have to be able to measure the charge flow. It's not totally straightforward. All right, so we're working our way towards climate. So climate involves all these things we've been talking about. The problem is, well, climate's a really loaded word. It's different from weather. I can tell you guys, like already, even just mentioning the word climate right now, I always put these videos on YouTube. They always put little signs underneath my YouTube videos telling you that, whatever this guy's telling you about climate, there's like, the UN knows what's going on with climate. Don't listen to this guy. I'm not even talking smack about climate either. They got these AI algorithms loaded because it's like such a well-defended concept, right? Because they don't want the climate change deniers coming after people's brains and ruining them. Now, that may be all well and good because I can guarantee you that when people talk about climate, for the most part, they're talking about taking care of the planet, which is absolutely a great idea, and we should probably figure that out. But climate refers to these overall patterns that change, mainly in the temperature, but also the humidity and precipitation levels of the planet across eons, right? So when you see these like headlines where they're like, the hottest day on record last week or whatever, climate's changing, it's like, that's ridiculous because weather and isolated individual events that happen like this, even over the course of years, are not the same thing as climate. So there's been something really interesting. This is where I was supposed to start today's lecture. I'm well past there, so let me skip ahead. There's been something really interesting where people have fixated on this idea that the Earth is getting warmer. And certainly what's at the heart of this situation is that the Earth definitely does go through these really interesting cycles. I mean, I'm going to jump ahead. I'll come back to this in a second. But if we look back, let's see here. Yeah, here's a great one. If we look back across the past million years or so, this is 500,000 years, we can see that there's these regular moments where there's huge glaciers at the poles, and then it contracts and it's very warm, and there's really not much in the way of glaciers at the poles. This has been happening for a long time. Not forever, though, but it's been happening for several millions of years. And these are very regular. They're about every 100,000 years you get a new cycle of this. Now, if you look at where we're at today, this is more or less the temperature map. We'll talk about how they derive temperature and all this stuff. We're kind of running par for the course for this whole thing, as far as I can tell. It's unclear whether it's going to go up or down, but we're actually quite a bit cooler right now than we were during the last warm period, which was back, 150,000 years ago, something like that. So the reason that people are freaked out is because they look around at the world and they see things that are not so good about our ecosystem. And I actually just, like I told you guys, I was in Maui a couple weeks ago. I was snorkeling, and the last time I went snorkeling in the tropics was when I was a kid. And I can tell you guys, without a doubt, that the coral systems are completely gutted. Like, it is nuts compared to when I was a little kid. And so I went and read about it, and it's something like 50% of the coral has died since 1985. Like 50%. It's really crazy. Now, the tragedy of it is, you might ask, like, why is that happening? The tragedy of it is that there's a lot of reasons that that's happening. Not the least of which is hundreds, if not thousands, of chemicals that aren't really being studied, that are flowing largely as industrial and agricultural waste into the rivers around the Great Barrier Reef, just flowing out. Even if you go to the coast here in Oregon, you can see where these paper mills and stuff are dumping garbage into the ocean. It's not a good situation. And so while people are very much fixated on this, it's very hip to focus on this idea of climate change, particularly with respect to this one molecule named CO2, which we're going to talk about in a second. There's a lot of things going on Earth right now which we absolutely have control over that aren't getting a lot of attention. And that's really scary to me, because I think that they're probably as important, if not more important, than the ones that are getting a lot of attention. So, for example, we'll get to CO2 in a second, but how much, do you guys know what percentage of the atmosphere is carbon dioxide?
Did we just get to like 4.2?
Any other ideas?
I thought it was like 2 originally.
Anybody else? Percentage of the atmosphere. So carbon dioxide is actually 0.04% of our atmosphere. Yeah, it's a very, very small piece of the puzzle, actually. And water is an extraordinary greenhouse gas as well, which is, much more abundant. So there's a lot of players, even if we want to just look at this greenhouse phenomenon, which I think is probably important, but I actually have this sneaking suspicion that there's more important things that we should be paying attention to. And they sort of missed the point. There's also this other angle that I wanted to read you guys a little bit about, which kind of scares me about this whole topic too, to some extent, because there's sort of this, there's the danger of thinking that, often when I talk to environmentalists and stuff, I sometimes get this narrative like, well, if we just had less people on the planet, like that would take care of things. And I'm very suspicious of that. And you guys, you might think I'm exaggerating. This was printed in the LA Times. This is a review of this book by Bill McKibben, which is called The End of Nature. Now look, this thing's written with it has the best intentions in some sense, which is like, hey, we should stop destroying our backyard, essentially, which is a great idea. But unfortunately, these conversations kind of sometimes go in this really weird direction. This guy writes, this is in review of the author. McKibben is a biocentrist, and so am I. We are not interested in the utility of a particular species or free-flowing river or ecosystem to mankind. They have intrinsic value, I agree. More value to me than another human body or 1 billion of them. I'm like, good God. Then he goes on, human happiness and certainly human fecundity are not as important as wild and healthy planet. I know social scientists who remind me that people are part of nature, but that isn't true. Somewhere along the line, about 1 billion years ago, maybe half that, we quit the contract and became a cancer. We have become a plague upon ourselves and upon the earth. Yikes, like, this is crazy. I mean, I understand to some extent the motivation. When you go and swim with these corals and you see the fish all gone and everything, it's really hard not to actually feel like physically anxious about it. He goes on, it's cosmically unlikely that the developed world will choose to end its orgy of fossil energy consumption. In the third world, its suicidal consumption of landscape. Until such a time as Homo sapiens should decide to rejoin nature, some of us can only hope for the right virus to come along. Ah, my God. So, like, the reason I bring this up is because I think that we have to really temper our outlook on these matters and be very clear about what's happening. So, there's a lot of solutions that we, as a people, only have a chance of accomplishing if we're around to fight for them. If we just surrender and die, I don't know that the powers that be are going to make any of these good futures come out. And I certainly don't see humans as a virus. And there's been some really tragic foreign policy as a result of this. I don't know if you guys are paying attention to what was going down in the Eastern Asia with these. So basically, the different UN councils put these extreme taxes on people for burning things like propane and so forth. The result was that people in like Bhutan were actually freezing to death and starving because they couldn't cook their food, right? So I guess what I'm trying to urge you guys to do is, as we talk about climate, as we talk about the things that we need to change, we need to be really sensitive to the second, third order effects that are going to result from those implications. Yes, we want to make the planet a better place, but do we want to like destroy entire populations of poor people as we do it? It's probably a really bad idea. But if you're only thinking with like one thing in mind, like humans are destroying the world, like we have to stop us at all costs, it can get pretty gnarly, honestly, and some of the conclusions can become downright genocidal if we're not careful. So, with that in mind, how do we actually look at climate changing over the years? It's very tricky, actually. And so when we reconstruct these temperature graphs, what does that even actually mean? So to the best of our ability, what we've done is we've drilled out these huge rods of ice from the ice caps at either pole. And this gives us some access to information that's stored in the form of precipitation across the years, and in particular sedimentation as well. Little bubbles that contain gases, right, that we can actually dissolve and look at by different atomic means. And the result of that is a second order derivation of the climate in the past. It's not direct. It's not like you pull this thing out and it just reads you a scroll of what the climate was like. You actually have to make some assumptions. You have to analyze the way that you think that these isotopes have decayed in various regimes in order to give the abundances that you see, and then you try to reconstruct what the climate history looked like in the past to the best of your ability. Now, the result of that is we get these kind of graphs, which is, this is a little anxiety-inducing, I understand, but we have a few different readouts here. Now, the primary thing that's read out, if you guys can, I know you can't see this, and I'm really sorry, I just yanked this off Wikipedia, but this is how it works. You essentially have heavy elements of oxygen that are seen, and you have lighter isotopes of oxygen that are seen by mass spec. What's an isotope? Anybody? Yes.
It's an atom with a different number of neutrons.
That's right.
It usually has.
Heck yeah, that's exactly right. Thank you. So it's got a little bit more stuff in it. We don't have to get into the weeds about what a neutron is, although if anybody wants to hang out all evening, we can talk about that. So there's some atoms that are heavier, some that are lighter. They're both oxygen, and they can be separated out by mass spec, which is just a fancy science instrument. So what happens is the idea is that when there's a lot of sun, there's actually a lot of evaporation. That means there's a lot of precipitation also. So what happens is that the lighter elements get evaporated quicker. They end up, through various means at the polar ice caps and get deposited. And so you get a record of how the climate, the overall weather patterns have changed across hundreds of thousands of years. They then back calculate, they watch this rate as it's occurring today, and they compare that to the way that the temperatures work today, and then they try to back calculate what that might have meant in the past, okay? So we create these graphs, and the result of it is that we hope to be able to reconstruct this temperature map, and we also hope to be able to infer CO2 from the past based on the temperature, and based on some of these inclusions actually having carbon dioxide in them. Now, the problem is, you see our CO2 levels that are kind of gone off the chart over here. And this is, of course, I think this is the picture that's in your textbook, where the CO2 levels in the past are like way lower than they are in the present. Do we actually measure the CO2 in the past? It's like, sort of. We take those inclusions, we try to calculate how much loss would actually be natural just due to the fact that the ice is leaky to some extent. And then these measurements that we have down here are actually done with sensors on Earth today. So the Earth is, like I said, about 400 parts, where do we have it? Parts per million, ppm, which is 0.04% of the atmosphere. So the CO2, by this kind of estimate, where we're comparing a direct measurement to a second order estimate from the past, seems to be really high, relatively speaking. And so, there's this idea in political philosophy that people can only think about one idea at a time, right? It's like, I've talked to so many of these climate scientists. I talked to the head of Goddard's NASA Space Science Institute, who's like the climate authority for the free world. And, he'll never see this lecture, but he would hate it if I told you this. But, off camera, I've talked to this guy and I've been like, hey man, there's a lot of stuff we need to be worrying about besides this inert molecule that everybody's going nuts about. And he's like, yeah, well, that might be true, but people are dumb, we gotta basically, if people just focus on the CO2 thing, then they'll, stop using engines and everything else will follow as a result. It'll be really good. And I think I think people aren't dumb, actually. I think people are actually pretty smart, and they really want to know what's going on. So I'm going to run out of time here today, but I'm going to make a case for you guys that there's a lot of other things that are contributing to the death of that coral that have nothing to do with carbon dioxide next time. And maybe you guys can bring me your own stories, or maybe one of you is going to argue with me that it is only CO2, and we'll deal with that. At any rate, I hope we can take care of the planet. Yes?
I just had a quick question.
Yes.
I don't know if we're gonna get into this out of the next class or next week, but weather modification at all?
Yeah, let's do it. I have I've had lots of conversations with people about that. There's so much to be talked about here. I really want to hear from you guys too. I'm sorry that I was kind of rambling at the end. I just had so much I wanted to get out. Let's talk at the beginning of class. You guys have a stellar weekend, and we'll pick it up here.